In the previous episode, we saw something that looked like magic. A leak appeared in the network, and we saw it the same day, not in the next field campaign. But that is not magic. It is data infrastructure. Today we answer a very concrete question. Your hydraulic model is already built and calibrated. What does it need exactly to become a digital twin? First, and this is the good news, we do not start from zero. The twin is not built on a blank page. It is built on the hydraulic model you already have. The one we calibrated in episode 1. That is its base, its foundation. And here comes the most important warning of the whole episode. The twin does not fix a bad model. If the base is poorly calibrated, if the network on screen does not match the real network, the twin will only amplify that error. Now in real time, around the clock. Dirty data on top of a bad model does not give you a twin. It gives you noise, live. That is why step 0 is a model you can actually trust. If the base is the model, the pulse is the data. But it is not about measuring everything, everywhere. It is about measuring the right things at the right points. In our network, there are 3 measurements that do most of the work. First, pressure downstream of the PRV. That is the point where episode 1 detected the leak. It is the thermometer of the sector. Second, inflow to the sector. What comes in tells you how much is being consumed, and at night, how much is being lost. Third, tank level. It is the boundary condition of the whole system. With these 3 signals, critical pressure, inflow, and level, you already have a twin that breathes. The rest you add later, when it gives back more than it costs. Now, how often? Here we have to separate 2 things people tend to confuse. One is resolution, how often the data is recorded. The other is latency, how long that data takes to reach your database. For a monthly water balance, or to refresh the calibration, 1 reading per hour, arriving once a week, is perfectly fine. That is a well-fed model. But remember the leak from episode 1, between 6 and 9 in the evening. With weekly data, you would have seen that leak on the next site visit. In other words, you would have gone back to the photograph. To see it today, you need resolution in minutes and latency in minutes. That, and nothing else, is the line between a model that updates and a twin that lives. And that data, how does it get there? Let us make the full journey. It starts at the sensor, in the field, a pressure transmitter, a flow meter. That sensor connects to a logger, an RTU, or a data logger, which digitizes it. From there it travels over communication, radio, cellular, sometimes fiber, to the SCADA system or a cloud platform. And finally, it is stored in a historical database, what operators call the historian. That historian is the memory of the system, and it is precisely the source the twin will read from. Every link in that chain can fail, and when it fails, very often it does not stop sending data. It sends bad data, and that is what we talk about next. Here's the step almost no one shows, and it decides whether the twin works or not. Data cleaning. No sensor sends a perfect signal. What arrives looks more like this. See these gaps? Those are null values. The sensor did not report. See this impossible spike? That is an outlier. A pressure of 100 meters that does not exist in this network. And see this flat, frozen stretch? That is a stuck sensor, repeating the last value even though reality changed. If the calculation engine eats this raw signal, it returns garbage, but with great confidence. That is why between the historian and the engine, there is a layer that validates, that fills in, that filters. This, once clean, can actually feed the twin. The quality of the twin will never be better than the quality of this step. We have a model. We have good data. What is missing is what truly makes it a twin, the engine that never stops. In the classic model, you open the program, run the simulation, look at the result, and close it. In the twin, that happens on its own, in the background, again and again. A new data point arrives, the hydraulic engine runs the model, compares simulated against measured, and if something diverges, it alerts. This is the loop that closes everything. Measure, ingest, clean, simulate, compare, and again. Without anyone having to press a button, you can build that engine with digital twin platforms or by automating your own hydraulic solver. It is exactly what I am building with Flow Analyzer. The model running on its own, against the data, all the time. So what does it take for a model to become a twin? 4 pieces. A calibrated base you trust, the right signals, at the right frequency, an ingestion that cleans the data before using it, and an engine that runs on its own, non-stop. Put those 4 together, and the photograph starts to move. In the next episode, the most interesting part, the decisions that only the twin makes possible. This episode was made with the assistance of Claude Code. If you manage a water network, subscribe to Transparent Blue Water, and I will see you in the next one.